Close your eyes for a moment and try to imagine cold. Not the cold of a winter morning, not the cold of ice pressed against skin, not even the cold of the deepest Arctic night. Try to imagine a cold so complete, so absolute, so fundamentally different from anything you have ever experienced that the word itself barely applies. A cold that is not a sensation, not a temperature measured on any scale your body understands, but the near total absence of the thing that makes warmth possible at all. The absence of motion. The absence of energy. The absence of almost everything. That is what space is, and it is stranger than you think. We say space is cold as if we are describing weather, as if the cosmos were simply a very large refrigerator, and the stars are the warm spots and the darkness between them is where the chill settles. But that picture is wrong in almost every important way. Space is cold for reasons that have nothing to do with wind or air, or the kind of cold you feel when you step outside on a January evening. Space is cold for reasons that reach down into the foundations of thermodynamics, into the quantum structure of energy itself, into the dying afterglow of an event that happened nearly 14 billion years ago. When you understand why space is cold, you understand something profound about the universe, about what it is made of, how it began, and where it is going. Let us start with a question that sounds simple but leads somewhere remarkable. What is cold? In the everyday sense, cold is a feeling. It is what your skin reports when it encounters something with less thermal energy than itself. But touch a block of ice, and it feels cold because heat is flowing out of your hand and into the ice, not because the ice is somehow reaching into you and stealing your warmth. Cold is not a thing in itself. It is an absence, the absence of thermal energy. And thermal energy at the most fundamental level is motion, the jiggling of atoms and molecules, the vibration of particles in a lattice, the kinetic energy of matter at the microscopic scale. Hot things are things whose constituent particles are moving fast. Cold things are things whose particles are moving slowly. And the coldest possible thing, absolute zero, the theoretical floor of temperature, would be a thing whose particles have stopped moving entirely. Absolute zero is 0 Kelvin. On the Celsius scale, that is negative 273.15 degrees. Whilst on the Fahrenheit scale, it is negative 459.67 degrees. It is a number that exists in the equations of thermodynamics as a hard boundary, a wall you can approach but never reach, because the laws of physics conspire to prevent any physical system from ever achieving it completely. The closer you get to absolute zero, the harder it becomes to remove that last tiny residue of thermal energy. The last traces of warmth cling to matter like the final embers of a fire that refuses to go entirely dark. Now, the average temperature of the universe, the number that cosmologists have measured with exquisite precision using sensitive instruments pointed at the sky, is 2.725 Kelvin. Just barely, almost negligibly above absolute zero, not the absolute floor of cold. But close enough that the difference would barely register on any thermometer you have ever touched. Where does this number come from? It does not come from the stars. It does not come from galaxies or gas clouds or any of the familiar structures we associate with the cosmos. It comes from something older and stranger than any of those things. It comes from the Big Bang itself, or more precisely, from the fading memory of the Big Bang, the echo of creation that is still reverberating through the universe nearly 14 billion years later. In the first moments after the Big Bang, the universe was unimaginably hot. Not 2.7 Kelvin, not thousands of Kelvin, not millions. In the earliest fractions of a second, yet the temperature of the universe was measured in the tens of billions of degrees, hot enough that matter itself could not exist, that the distinction between particles and energy was meaningless, that the entire cosmos was a seething, undifferentiated plasma of pure energy and proto-matter. There were no atoms, there were no stars. There was only heat, almost infinite heat, compressed into a space smaller than anything we have words to describe. As the universe expanded, it cooled. This is a basic thermodynamic relationship. When a gas expands, it cools. When you release compressed air from a tire, it feels cold against your skin because the same principle is operating in a familiar everyday context. The universe is, in a sense, the most extreme example of this process ever observed. And it expanded from almost nothing to an unimaginable vastness, and as it did, it cooled from billions of degrees toward the quiet chill of 2.7 Kelvin over nearly 14 billion years. The light that was produced in that early hot phase, the radiation that filled the young universe like the interior of a star, bouncing off particles of plasma in every direction, that light is still here. It has not gone anywhere. It cannot go anywhere, because it is everywhere. As the universe expanded and cooled and the plasma condensed into neutral hydrogen atoms about 380,000 years after the Big Bang, the radiation that had been trapped in the plasma was suddenly free to travel. It streamed outward in all directions, filling the expanding cosmos with a bath of light. And as the universe continued to expand over the following billions of years, that light was stretched, its wavelengths lengthened by the expansion of space itself, shifting from visible light to infrared, then to microwave radiation, cooling as it went. Today, that ancient light fills the entire observable universe as a faint, uniform haze of microwave radiation with a temperature of 2.725 Kelvin. We call it the cosmic microwave background, and it is one of the most important things ever discovered. The cosmic microwave background was first detected in 1965 by two radio astronomers named Arno Penzias and Robert Wilson, who were working with a large horn antenna at Bell Telephone Laboratories in New Jersey. They were trying to eliminate a persistent its mysterious noise in their equipment, a faint hiss that seemed to come from every direction equally, regardless of where they pointed the antenna. They cleaned pigeon droppings out of the antenna, suspecting the birds were responsible. They checked and rechecked their instruments. The hiss remained, uniform, constant, inescapable. It took a conversation with cosmologists at Princeton to reveal what they had stumbled upon. The afterglow of creation itself, the oldest light in the universe, still whispering from every direction after nearly 14 billion years of travel. They won the Nobel Prize in Physics in 1978. So the temperature of space, 2.725 Kelvin, is not some intrinsic property of the void. It is the temperature of this ancient radiation, this cosmic relic. This electromagnetic ghost of the Big Bang still permeating every cubic centimeter of the universe. It is the universe's own memory of how hot it once was, faded almost beyond recognition by billions of years of expansion. But here's the first of the strange truths that takes this story deeper. 2.7. Kelvin is an average. It is the temperature of the radiation field. But temperature is a concept that technically requires matter, particles, to have full meaning. And space, the space between stars and between galaxies, is not truly empty, but it is extraordinarily close to it. The density of matter in intergalactic space, the vast regions between galaxy clusters, is estimated at roughly 1 hydrogen atom per cubic meter. 1 atom per cubic meter. That is a vacuum so extreme that any laboratory on Earth would consider it essentially perfect. When we say space has a temperature of 2.7 Kelvin, we mean the radiation field has that temperature. The matter, the vanishingly sparse matter that actually occupies interstellar and intergalactic space, is another story. And this brings us to something deeply counterintuitive about what cold really means in the cosmos. If you were somehow transported instantly into deep interstellar space, far from any star, far from any source of radiation other than the cosmic microwave background, what would you experience? You might think you would feel cold immediately, unbearably, instantly cold. After all, the surrounding temperature is only a few degrees above absolute zero, but the reality is more complicated, and in some ways more frightening. You would not feel cold in the way you feel cold on a winter day. Cold on Earth reaches you primarily through convection, through air molecules striking your skin and carrying your body heat away. In space, there is no air. There is essentially no matter at all to conduct heat away from your body. The physical mechanism by which cold normally works, the transfer of thermal energy through direct contact with a cooler medium, would be absent. Instead, you would lose heat through radiation. Every object above absolute zero emits electromagnetic radiation, infrared light, at a rate determined by its temperature and the nature of its surface. This is called thermal radiation, and it is the mechanism by which the sun warms the Earth from 93 million miles away. And in the absence of any other heat source, and in the absence of any conductive medium, your body would slowly radiate its heat into space, losing energy as infrared photons until your temperature equilibrated with the surrounding radiation field. This process is slow, surprisingly slow. Without the convective cooling of air, a human body in deep space would take a surprisingly long time to freeze, far longer than is commonly depicted in science fiction, where characters exposed to the vacuum of space freeze instantly. The actual physiological threats of space exposure are more immediate and more gruesome than cold: the absence of pressure, causing dissolved gases in the blood to form bubbles; the absence of oxygen; the exposure to unfiltered solar radiation and cosmic rays. Cold is not the first thing that kills you in space. Oh, it is not even close to the first thing. But given enough time, in the deep dark far from any star, the radiation loss would indeed cool a body toward 2.7 Kelvin, unless something else intervened. Because space is not uniformly cold, not even close. Near a star, the temperature of space is not 2.7 Kelvin. It is not cold in any meaningful sense. The space between Earth and the Sun is bathed in solar radiation intense enough to heat exposed surfaces to hundreds of degrees Celsius on the sun-facing side. Astronauts working outside the International Space Station can experience temperature swings of more than 300 degrees between the sunlit side of their suits and the shadow side. The suits themselves are engineering marvels designed not primarily to keep astronauts warm, but to manage this extraordinary thermal gradient, to wick away heat on one side and retain it on the other, maintaining a livable temperature in between. On the Moon, this effect is dramatic and direct. The lunar surface in full sunlight can reach about 120 degrees Celsius, hotter than boiling water. The lunar surface in shadow, or on the night side, plunges to negative 170 degrees Celsius. These swings happen because the Moon has no atmosphere to moderate them, no air to hold heat, redistribute it, smooth out the extremes. The Moon experiences the raw physics of radiation, unmediated by any protective layer of gas, and the further you go from any star, the colder things become. The outer planets of our solar system are frigid by any measure. Neptune, the farthest planet from the Sun, and has an average temperature of about negative 214 degrees Celsius, 59 Kelvin. Its largest moon, Triton, is one of the coldest measured objects in the solar system, with a surface temperature of about 38 Kelvin. Triton's thin nitrogen atmosphere partially condenses onto its surface in winter, freezing solid, then sublimating back into gas as the season changes. But all of these temperatures, as extreme as they sound, are still warm compared to some of the environments the universe contains, because there are places in the cosmos that make the outer solar system look almost balmy, places that approach absolute zero in ways that challenge our understanding of what matter can do and what the laws of physics permit. The Boomerang Nebula is perhaps the most famous of these extreme cold environments. It is a pre-planetary nebula located about 5,000 light-years from Earth in the constellation Centaurus, formed from a dying star that ejected its outer layers with extraordinary speed, roughly 164 kilometers per second. That is fast, extraordinarily fast for an expanding gas cloud. And it is that speed, that extreme rate of expansion, that makes the Boomerang Nebula something without parallel in the known universe. When a gas expands rapidly, it cools. We established this with the analogy of compressed air. The Boomerang Nebula is expanding so rapidly that it has cooled to approximately 1 Kelvin, colder than the cosmic microwave background itself. 1 Kelvin, 1 degree above absolute zero. The nebula is, as far as we can tell, the coldest naturally occurring place in the observable universe. But colder than the void between galaxies, colder than the darkest reaches of interstellar space, colder than virtually anything that has existed since the first moments after the Big Bang. Let that settle in for a moment. A nebula, a cloud of gas produced by a dying star, is colder than the background temperature of empty space. The expanding cosmos, the fading afterglow of creation, maintains a temperature of 2.7 Kelvin everywhere. And this nebula, this particular cloud of gas 5,000 light-years away, has gone colder than the universe itself. This is possible because the cosmic microwave background is radiation, photons, not matter. The nebula's gas has expanded and cooled faster than the radiation field can warm it back up. In a sense, the nebula has locally outrun the universe. It has expanded so quickly that it has temporarily beaten the baseline temperature of the cosmos, dropping below the floor that the Big Bang's afterglow maintains everywhere else. It will not stay cold forever. Eventually, as the expansion slows and the nebula disperses, the cosmic microwave background will warm whatever remains back to 2.7 Kelvin. The universe has a kind of thermal baseline it enforces on timescales long enough for radiation to do its work. But for now, the Boomerang Nebula is a cold spot in an already frigid cosmos, a singular extreme in a universe full of extremes. And yet the coldest temperatures that exist in the universe may not be natural at all. They may be the ones that human beings have deliberately created in laboratories on Earth. The quest to reach absolute zero has been one of the driving projects of experimental physics for more than a century. As early as the 1870s and 1880s, physicists were racing to liquefy gases that had previously been thought to be permanent, oxygen, nitrogen, hydrogen, by cooling them under pressure to the temperatures at which they condensed into liquid. These were considered almost impossibly difficult experiments at the time, requiring machinery of tremendous precision and cooling systems of great complexity, all to achieve temperatures that are now considered relatively warm by the standards of modern low-temperature physics. By the early 20th century, the Dutch physicist Heike Kamerlingh-Onnes had succeeded in liquefying helium, the most difficult of all gases to condense, at about 4.2 Kelvin. And he went on to make one of the most important discoveries in the history of physics: superconductivity, the phenomenon by which certain materials, when cooled below a critical temperature, lose all electrical resistance entirely and allow current to flow without any energy loss whatsoever. Onnes discovered this in mercury at about 4 Kelvin in 1911, and it launched a field of research that continues to produce stunning discoveries more than a century later. Superconductivity is, in its way, one of the most beautiful manifestations of what extreme cold does to matter. At ordinary temperatures, electrons moving through a metal collide with the vibrating lattice of atoms, losing energy as heat. This is electrical resistance, the reason wires get warm when current flows through them. But at sufficiently low temperatures, in superconducting materials, the electrons pair up through a quantum mechanical phenomenon. They form what are called Cooper pairs, and these pairs move through the lattice without interaction, without resistance, without energy loss. It is as if the cold has calmed the universe enough for quantum order to emerge from thermal chaos. Modern superconducting magnets, cooled to near absolute zero with liquid helium, are the engines at the heart of magnetic resonance imaging machines in hospitals around the world, of the Large Hadron Collider at CERN, of experimental fusion reactors, and of a growing number of technologies reshaping medicine, energy, and physics. The extreme cold of space, reproduced in laboratories, is not merely a curiosity. It is a working technology, a tool, and a state of matter that reveals physics unavailable at any other temperature. But laboratory physicists have gone far colder than liquid helium. In the latter decades of the 20th century, techniques were developed using lasers to cool individual atoms, a process called laser cooling, which seems paradoxical at first glance because we associate lasers with heat. The trick is subtle. A laser tuned to just the right frequency can slow an atom down by repeatedly bouncing photons off it in a way that reduces its kinetic energy with each collision. An atom moving randomly in a gas is being jostled constantly by thermal energy. Hit it with enough photons at the right energy, enough times, and you can slow it almost to stillness, cool it almost to absolute zero, using laser cooling combined with other techniques, evaporative cooling, magnetic trapping. Physicists have achieved temperatures in the laboratory of a few billionths of a Kelvin above absolute zero. Billionths. The numbers at this scale become almost meaningless to ordinary intuition. These are temperatures lower than anything that naturally occurs anywhere in the observable universe. Colder than the Boomerang Nebula, colder than the spaces between galaxies, colder than anything the cosmos itself has managed to produce since the first moments after the Big Bang. And at these temperatures, matter does something extraordinary. It stops behaving like ordinary matter at all. When a gas of atoms is cooled to within billionths of a degree of absolute zero, something quantum mechanical happens. The atoms begin to lose their individual identities, their quantum wave functions, which at higher temperatures are tightly localized around each individual atom, begin to spread out and overlap. The atoms, in a quantum mechanical sense, begin to occupy the same state. They collapse into a single quantum entity, a superatom, in which all the component atoms behave as one coherent whole. This state of matter is called a Bose-Einstein condensate, predicted theoretically by Einstein and Indian physicist Satyendra Nath Bose in 1924 and 1925, but not achieved experimentally until 1995, when Eric Cornell and Carl Wyman at the University of Colorado cooled a gas of rubidium atoms to about 170 billionths of a Kelvin and watched it happen. A Bose-Einstein condensate is not a solid, liquid, gas, or plasma. It is a fifth state of matter, a quantum state that only exists near absolute zero, that in which the boundary between individual particles dissolves, and the quantum mechanical wave nature of matter becomes not just detectable but dominant, visible, macroscopic. The cold has revealed a layer of reality normally hidden beneath thermal noise, a layer where quantum mechanics operates not on the scale of atoms, but on scales we can see and manipulate directly. What does this tell us about cold itself? It tells us that temperature is not just a measure of comfort or danger. It is a measure of how much quantum order is hidden beneath thermal chaos. At high temperatures, thermal fluctuations overwhelm quantum effects, and matter behaves classically, atoms and molecules moving independently, randomly, like billiard balls in a box. As temperature falls, the noise subsides, quantum effects emerge, structure appears, the weird, counterintuitive, beautiful physics of the very small begins to express itself at larger and larger scales. Cold is a lens, a way of seeing through the thermal fog of everyday existence into the quantum mechanical underpinning of reality. The experiments conducted near absolute zero are not just engineering exercises. They are a way of peeling back a layer of the universe, of exposing structures and phenomena that exist at all temperatures, but can only be clearly seen when the thermal noise is quieted almost to silence. Now let us turn that lens outward again, back to the cosmos. Because the cold of space is not merely a backdrop to the story of the universe, it is an active participant. It is, in a deep sense, the destination toward which the universe has always been moving. One of the most important and strange facts about cold in the universe is this: the universe is getting colder. Not quickly, not in any way detectable on human timescales. But the cosmic microwave background is cooling as the universe expands. Its temperature has been dropping since the moment that ancient radiation decoupled from matter, 380,000 years after the Big Bang. It was about 3,000 Kelvin then, warm enough to glow a dull red like a dying ember. Over the subsequent 13.5 billion years, the expansion of the universe has stretched its wavelengths and dropped its temperature by a factor of more than 1,000 to the 2.7 Kelvin we measure today. In the far future, as the universe continues to expand, the cosmic microwave background will cool further still. In 1 trillion years, it will be a tiny fraction of a Kelvin. In tens of trillions of years, as the last stars exhaust their nuclear fuel and go dark one by one, the universe will be approaching a temperature indistinguishable from absolute zero. Not because any active cooling process is removing energy, but because the expansion of space is diluting and stretching what energy remains, spreading it ever more thinly across an ever greater volume, reducing its density toward nothing. This is the long, slow death that cosmology projects for the universe. Not a dramatic explosion, not a collapse back into a hot singularity, though some models allow for such a possibility. The standard picture describes an end that is quieter and more profound than any explosion, a gradual dimming, a slow settling toward cold. At an approach toward absolute zero that takes unimaginable spans of time. Physicists call this the heat death of the universe, a somewhat misleading name since it describes not a hot death, but a cold one. A state of maximum entropy in which all energy is evenly distributed, no gradients exist to drive any process, no work can be done, no information can be processed, no thought can occur. A universe at thermal equilibrium, at a temperature infinitesimally above absolute zero, in which nothing happens because nothing can happen. This fate is almost beyond comprehension in its timescale. The current age of the universe is about 13.8 billion years. The final evaporation of the last black holes, through the slow quantum process called Hawking radiation that Stephen Hawking predicted in 1974 would occur on timescales measured in numbers with 100 digits or more. So far in the future that the number of years cannot be meaningfully written out or comprehended. The stars will all have died long before. The galaxies will have dissolved. The last structures of ordinary matter may themselves have decayed, protons dissolving into lighter particles and radiation over timescales that dwarf even the black hole evaporation era. After all of that, what remains? Quantum mechanics and thermodynamics conspire to suggest a cold, dark, nearly featureless void, perhaps a trace of radiation so dilute it barely qualifies as energy. It's a universe so close to absolute zero that the distinction is philosophical rather than physical. The heat of the Big Bang, which ignited everything, has been spent. The loan has been repaid. The expansion has done its work. The cosmos rests in the closest thing to nothing that physics permits. There is something deeply affecting about sitting with this fact, about feeling warmth, the warmth of a room, of sunlight through a window, of your own living body, and knowing that this warmth is temporary in the most fundamental sense, not temporary the way a season is temporary or the way a civilization is temporary the way the entire universe is temporary. The heat you feel is a remnant of the Big Bang, slowly being redistributed into the cold of the expanding void as it always has been and always will be. Until there is no gradient left to drive the process. And yet, there is another way to hold this thought, because in the vast cold of the universe, in that near-universal darkness and chill, something happened that has never been fully explained. In certain places, around certain stars, on certain small, rocky, wet worlds, matter organized itself. Atoms formed molecules. Molecules formed larger structures. Those structures developed the ability to capture energy from a local source of warmth and use it to maintain their own organization against the incessant pressure of entropy. Life emerged, and life, eventually, developed the capacity to ask questions, to measure temperatures, to detect the cosmic microwave background and understand what it meant, to calculate the fate of the universe and feel something about that fate, wonder, or melancholy, or a deep and quiet peace. In the entire observable universe, with its hundreds of billions of galaxies and its hundreds of billions of stars per galaxy and its countless planets, we know of only one place where this has definitively occurred. One small planet orbiting one ordinary star on the outskirts of one unremarkable spiral galaxy. In the cold and dark of the cosmos, on this one world, life appeared and became curious and looked out at the cold and dark and asked why. That question, asked against the backdrop of 2.7 Kelvin, asked in a universe drifting slowly and inexorably toward its thermal death, may be the most extraordinary thing that has ever happened in the four-dimensional fabric of space-time. It is not just remarkable that life exists in the cold universe. It is remarkable that the cold universe is being observed and measured and contemplated by something warm enough to be troubled by its coldness, something that finds it beautiful. The cosmic microwave background is not just a temperature reading. When astronomers map it in precise detail, as the Wilkinson microwave anisotropy probe and the Planck satellite have done with extraordinary resolution, they reveal tiny variations in its temperature, fluctuations of about 1 part in 100,000, imprinted across the whole sky like the faintest possible pattern. These fluctuations are not random noise. They are the preserved imprint of quantum variations that existed in the first tiny fraction of a second of the universe's existence, amplified by the rapid early expansion into the seeds of all structure. The seeds from which galaxies grew, the seeds from which stars condensed, the seeds from which planets formed around those stars, and from which, on at least one of those planets, something warm and curious and alive eventually arose. Every galaxy you have ever seen in a photograph, every star in the night sky, every mountain and ocean and living cell on this planet, all of it descended. Through billions of years of cooling and condensing and organizing, from slight thickenings and thinnings in the early plasma of the universe, still readable today as the faintest temperature variations in the microwave glow of 2.7 Kelvin. The cold of space contains, written in its structure, the blueprint of everything that exists, and it is still there, right now, everywhere. The room you are in is saturated with microwave photons at 2.7 Kelvin. Billions of them passing through you every second, passing through the walls, passing through the Earth itself, streaming in from every direction equally. The oldest light in the universe, carrying the memory of a fire that burned before this planet existed, before the sun existed, before any star existed, before atoms existed in the form we know them. It surrounds you as completely as anything can. You are, at this moment, immersed in the afterglow of creation. It is the coldest light there is, the most ancient, the most traveled. And it is here, always, the quiet background temperature of a universe doing what it has done since the beginning, expanding, cooling, very slowly. Now toward the absolute stillness that is the eventual destination of all things. Heat flows from hot to cold. That is one of the most inviolable principles in all of physics. The universe began unimaginably hot. The universe is cooling. The direction is fixed. The destination is cold. And the journey, measured in the fading temperature of that ancient microwave light, is already nearly 14 billion years old, with incomprehensibly more to go. The temperature of deep space, 2.725 Kelvin, barely above absolute zero. The number is simple, almost elegant, and the story it tells, when followed all the way from the first fraction of a second of the Big Bang through the formation of atoms and stars and galaxies and life, to the far future extinction of every source of heat in the cosmos, is the story of everything. Yet the whole arc of existence, described in the slow cooling of a universe that once burned with the heat of its own beginning. Step outside on a clear night and look up at the stars. Every photon of starlight that reaches your eye has traveled across an ocean of near absolute zero space, through the faint microwave bath of the cosmic afterglow, to arrive at this moment in your experience. Every star you see is an island of heat in an almost incomprehensibly cold universe, a temporary departure from the equilibrium toward which everything is slowly moving. The warmth of stars is borrowed time. The warmth of planets is borrowed time. The warmth of living things is borrowed time, taken from the nuclear fire of a star and converted, through the improbable chemistry of life, now into thought and memory and the capacity to look up and wonder at the dark. The cold is patient. It has been there since before the first atom formed. It will be there after the last star fades and the last black hole evaporates, and the last trace of structure dissolves into the expanding void. It is the universe's resting state, its default, its long-run equilibrium. Everything else, every burst of heat, every flare of starlight, every warm world, every living thing, every thought that has ever been thought, is a temporary fluctuation against that cold background, a brief and improbable departure from the baseline. And that improbability is everything. That the universe is mostly cold and dark and empty does not diminish the warm, bright, inhabited corners of it. It makes them extraordinary, the warmth of a living world. In the context of a universe drifting toward absolute zero, is not merely pleasant. It is the rarest thing in the cosmos. A local victory of order over entropy, of heat over cold, of complexity over simplicity, sustained for a cosmic instant against forces that will eventually, inevitably, win. So when you feel warmth, the warmth of sunlight on your face, the warmth of another person nearby, the warmth of your own living body maintaining itself at around 310 Kelvin, through the constant combustion of chemical fuel, remember what surrounds you. Remember the 2.7 Kelvin of the deep cosmos. Remember the 1 Kelvin of the Boomerang Nebula. Remember the billionths of a Kelvin achieved in laboratories where matter itself transforms into something quantum and strange and beautiful. And remember the absolute zero that no natural system has ever quite reached, but that everything is slowly, patiently, inevitably approaching. Remember that warmth in this universe is the exception. Cold is the rule. And you are, for this brief and unrepeatable time, impossibly, gloriously the exception. The darkness outside is cold, almost unimaginably cold. The kind of cold that existed before Earth formed and will persist long after the sun has died. It is out there right now, in every direction, the temperature of the universe's long memory of a fire that once burned everywhere and is still very slowly going out. And in the middle of all that cold, you are warm. You are here. And that, against the backdrop of the universe's near absolute zero void, is perhaps the most remarkable fact of all.